I'm going to solve a few problems that you need to know how to do for your final exam. So for RLC circuits, you need to know how to solve them using differential equations. But if you can get the circuit down to where it's just a series RLC or a parallel RLC, then those solutions are known and they're given here in this table. And so that can make it a little easier. You can just get it down to the series or parallel and then use these equations to help you solve it. You also need to know how to solve RLC circuits in the S domain. So hopefully you learned about Laplace transforms in your differential equations class or your math methods for engineers class. And this table gives us the Laplace transform pairs. So for example, if you have e to the minus at, its Laplace transform is 1 over s plus a. And if you have 1 over s plus a, its inverse Laplace transform is e to the minus at. So you use those when you're solving in the S domain. And my cat here is trying to change the screen. And you also need to know how to redraw the circuit in the S domain. And so you need to know these, how an inductor becomes an inductor plus a current, a voltage source in series or a current source in parallel, and similarly for a capacitor, and we're going to see how to do that. And so I think, I don't remember if the one we have is an inductor or a capacitor, but if you have the other one, you do it the same way. So once you learn the technique, you'll see how to do it. So this first one, I am sorry, my cat is right here. He's really trying to get involved. So for this one, we are going to use the S domain, and we are given that the voltage is given by this graph right here. And if you look at the graph, you can see, well, that's just the graph of V equals t, u of t, because it starts at time t equals 0. So it's just the straight line, so that's what that is. So this voltage source is tu of t. And we are first going to change this to the S domain. It does tell us, let's see, well, it doesn't tell us, but since we have that the function, the voltage, was 0 before time t equals 0, then that tells us what we need to know for drawing our inductor and our capacitor, that at 0 minus, the voltage at the capacitor was 0, so we won't have that voltage source. And at 0 minus, the current through the inductor was 0, so we won't have that voltage source. So we won't have these two voltage sources. Okay, so we're going to redraw this. So first, we take the Laplace transform of t, and the Laplace okay, I've got to get rid of this cat. Hold on. Okay, he'll probably come back. All right. The Laplace transform of t is 1 over s squared. So we're just going to use for this one that v equals IR. That's what we're going to use. But first, let's transform all of these to the S domain. So this will become, oh, he's back, 1 over s squared. The resistance remains the same. The resistance is still R. The inductor is L over S. And the capacitor is 1 over CS. And I apologize, my S's look just like 5s, and I'll do my best to make them separate, but it's going to be hard. Okay, so, and then in terms of numbers, that's 1 over S squared. And R is 2. And L is 6. Oh, did I write L over S? I think I was distracted by the cat. That's just LS. So that's 6S. and the capacitor is 1 over 2s. Okay, so now we can use Ohm's law and say V equals IR. So 1 over S squared equals I. Now the reason we go to the S domain is we can now just add these and treat them all like resistors. We can just add them. I times 2 plus 6S plus 1 over 2S. Okay. So now I'm going to start the calculator because it takes a while. I'm going to get a common denominator for these things in the parentheses. So the common denominator is S. So that's 2S over S plus 6S squared over S plus 1 over, or I'm going to bring the 1/2 up on top, so that'll make that 0.5 over S. So then this is 1 over S squared equals I times 2S plus 6S squared plus 0.5 all over S. So that's a 5. Thank you, kitty. All right, so now we want to solve for I. So I'll multiply both sides by the reciprocal of this. So I equals S over 2S plus 6S squared. No, Noah. I don't even know what he did. Okay. S over 6S squared plus 0.5 He's sitting over here and he is so pleased with himself. So 2S plus 6S squared plus 0.5 times 1 over S squared. So now the S cancels with one of these, and I have 1 over S times, I'll write this in order in terms of degree, 6S squared plus 2S plus 0.5. And now I'll factor a 6 out of that. So 2 divided by 6 is 1/3, so 1/3 S. Plus 1/2 divided by 6 is 1/12. Okay, so then now we need to factor that. So there's different ways of doing this. Depending on which math class you took, you may have learned how to complete this square and learn this and do this with a sine and cosine, and that way is fine. You'll end up with an answer that's slightly different looking than this, but it actually has the same value. I'm going to do it the way the book does it. I like the other way better, but over the years that I've SI'd this class, I think people like to do it the way the book does it. So I want to factor this, so I want to find the solutions. Now, if you did as I suggested at the beginning of the semester and got the TI 36, you will be pleased because this is the stage where it really helps do a lot. So, for instance, it will do the quadratic formula for us. So I'm going to go, there's a function polysolve. So it says TI30X up here. It's TI36X in the United States. So second and polysolve, and I want the quadratic. And A is 1, B is 1/3, C is 1/12, and it gives me the answer in A plus BI form. So we want that in A plus JB form. In case you were a little confused, J is just the electrical engineer's way of doing the square root of -1. So this, I'll press this arrow button to get it in decimal. So this is minus 0.166, and then the imaginary part is 0.2357. If I kept going, it would have an I at the end of it. So my solutions to the quadratic equation are, let me write them here. So the solutions are S equals, did I not get the right answer? Let's see. Oh, I did. S equals negative 0.17 plus J 0.236. I might just do that as 0.24. And I know, so that's one solution. The other solution is going to be negative 0.17 minus J 0.24. They always come in conjugate pairs, but the calculator will tell me that if I ask for the next solution. And I go over to the right, I'll see it's the same thing, minus 0.234. Okay, so that tells me then that this factors, so I have I equals, it factors into, let's see, I took out a 6, so I'm going to bring that 1/6 on top. So 1/6 over S times S minus this first one, so minus 0.17. Actually, when I do minus, it'll become plus. So plus 0.17 minus J 0.24. And then the second one is S plus 0.17 plus J 0.24. So when you have complex solutions, they always work out like that. Now, in order to do my inverse Laplace transform, I'm going to want to do partial fractions. So I know that this right here equals sum A over S plus B over S plus 0.17 minus J 0.24 plus C over S 0.17 minus J plus J 0.24. Now, to find A, I'm going to plug, I see my third solution. So when I solved this quadratic equation, I got the solutions minus 0.17 plus J 0.24 and minus 0.17 minus J 0.24. I had a third solution. That third solution was 0. So that, I can say S3 equals 0. And that came from this S right here. So to find out what A is, I take my original fraction, 1 over 6 S plus 0.17 minus J 0.24 and S plus 0.17 plus J 0.24. And I plug in 0, only I take out this S term. Because if I plug in 0 to that S term, I'll get something over 0, and that's not that's undefined. That's just how I remember it. That's not why it works, but that's how I remember it. So I plug 0 into this, and you get, so this is what A equals. So A equals 1/6 over, and you plug 0 into this, 0.17 minus J.24, and 0 into this, 0.17 plus J.24. And that gives, so, and you can do this on this calculator. So I would do let's see, so I get a fraction, and on the top of the fraction I'll have 1/6, and on the bottom of the fraction I'll have open parentheses 0.17 plus, now it's going to be I on the calculator, I times 0.24 and 0.17 minus I times 0.24, and I get 1.93 plus 0I, and I do expect to get zero imaginary part because these are conjugates of each other. Actually, when I did this earlier, I think I took it out to more decimal places, and I got 1.97, so I'll use that. That's just when I used 0.236 instead of 0.24, but either way is fine. So just what I have in my notes. So I'm going to say 1.97. Okay, now to find B, we're going to do the same thing. We take B equals 1/6 over S times S plus 0.17 minus J.24, and S plus 0.17 plus J.24. And we are going to plug in the solution that we get from this denominator, or whatever makes that denominator equal to 0. And what makes that denominator equal to 0 is minus 0.17 plus J.24. That is where this solution came from. So if you go back and you look, and we had this was our solution, and then we said minus that came up with this factor in the denominator, and so that's where this is coming from. So I'm going to plug in that S equals minus 0.17 plus J.24, but I cross out this term because that's the term that would make it equal to 0. So I have 1/6 over minus 0.17 plus J.24, and then I plug this in for S, so minus 0.17 plus J.24, plus 0.17 plus J.24. And you can see that the minus 0.17 and plus 1.7 cancel each other out, so that can save you a little bit of calculation. And then we'll have 1/6 over minus 0.17 plus J.24 times J.24 plus, how do you think I could get this, J.24 0.24. And I get that B is minus 0.96 plus 0.682. Now I'll write that down. B equals minus 0.96 plus J.68. Okay, but we're going to want this in polar form. So I'm going to show you once how to do it in polar form by hand, but then, I'm going to show you first how to do it on the calculator, then I'll show you how to do polar form by hand, and then I'm just going to use the calculator after that because it's a lot easier. So here I have my answer, so I've got my answer, and I want to convert that to polar. There's a complex menu here, so second complex, convert to polar, gives it in r theta form, and that tells me that there's two ways to write this. You can write this as I'll show you both ways. So this is 1.18 angle 144, so you can write it as 1.88 angle 144. Or to make it match the forms that you have on your Laplace transforms, you can write it as 1.88 e to the j 144, and those are equivalent. And you'll be using these a lot, these forms a lot in circuits 2 and power. And I am going to show you how to do this conversion in case your calculator doesn't do it, but I strongly recommend that you get this calculator. I told you this at the beginning of the semester. Just saying. Alright, so what you do to convert it otherwise is you draw an axis, and this is the y-axis is the imaginary axis, and the x-axis is the real axis. And our real part was minus 0.96, so minus 0.96. Our imaginary part was 0.68, so 0.68. And then you draw that vector that goes to that point. That's a weird color. It goes to that point. Okay, and then you find the magnitude of that vector. So the magnitude is the square root of 0.96, well, negative 0.96 squared, but when you square it, it'll be positive, plus 0.68 squared. So second square root, what was it, 0.96 squared plus 0.68 squared, enter, and we get 1.18. So 1.18 was the angle that we wanted, the magnitude that we wanted. That's this part right here, so that's the magnitude. Now we need to get the angle, and this is why it's important to draw the vector to find out exactly what the angle is, because if you just start taking like inverse tangents, then you might not end up with the correct angle. You want the angle coming from the positive x-axis. So I'm going to look at this triangle right here, that's this one, that has 0.96 on this side and 0.68 on that side. And I'm going to say theta equals so this is the angle I'm getting. Theta equals the inverse tangent of 0.68 over 0.96. Let's see, am I in degrees? Yes. So inverse tangent 0.96 divided by 0.68, and I get 54.69 degrees. So that tells me that this angle is 54.69 degrees. but the angle that I actually want, which is the angle from the positive axis, is going to be 180 degrees minus 54.6, whatever that was, 9 degrees. So 180 minus that is not giving me the right answer. So hold on. You see, if we were doing this live, you could have said, hey, dummy, you're doing the wrong ones. So the opposite is 0.68 and adjacent is 0.69. Oh, wait, that's what I wrote here. Did I just not do it that way on the calculator? I just did not do it that way on the calculator. So the inverse tangent of, get it right this time, 0.68 over 0.96. 0.68 divided by 0.96. And that gets me 35.3 degrees. And then if I subtract that from 180, I get 144.7. Okay, now if you did, say, the inverse tangent of negative, or 0.68 over negative 0.96, that would have gotten you the angle in the fourth quadrant, when in fact we wanted the angle in the second quadrant. So that's why I always use, I'll just show you. So if I did trying to be fancy and messing up. So it gives me negative 35. So it gives me the angle in the fourth quadrant instead of the second quadrant, which, depending on your purposes, may work just fine. But I always prefer to draw it out, look at the triangle, and figure out what we've got. So we found that B is 188 e to the j 144. Luckily, we are almost done with this problem, because once we have B, we automatically have C. They always come in conjugate pairs. So C is going to be, if B is 1.88 j 144, then C is 1.88 e minus j 144. So at least there's that. That is helpful. Okay, so now to get back to the reason we were doing all this was for getting partial fractions. So we rewrote this now, and we have partial fractions, and so we can rewrite I in terms of three fractions here that we can then take the inverse Laplace transform of. So let's do that. Wonder why I did that. That's okay. Alright, so now we can rewrite this as, now we had, don't forget we had oh, no we don't. We took that into account. So ignore that last statement. We're really almost done. So we got just 2 more steps. So I equals 1.97 over S plus 1.18 J to the 140 J, that's not J, 1.88e to the J144 over S plus 0.17 plus J.24 plus 1.18 e to the minus J144 over S plus 0.17 minus J.24. Now we need to take the inverse Laplace transforms of these. So when we take the inverse Laplace transforms, we're going back to the t domain. So the inverse Laplace transform of 1 over s is t. So 1.97 t. To get the inverse Laplace transform of everything else here, let's go back and look at our Laplace transform pairs. And you see that if you have this form, well, there's no telling where it pasted it. Alright, so let's just take a look at it. So when you have e to the j theta plus e to the minus j theta over e plus a plus jb, then the a part is going to be in the exponent of the exponential. The b part is going to be the coefficient of the t in the cosine bt, and the theta is the phase shift in that cosine, and there's a 2 out in front. So going back and looking at what we have here, then we have plus 2 times 1.18, there's the 2 from out in front, e to the minus 0.17t, so it's minus that, cosine, and then the coefficient is 0.24t, and then plus 144 degrees. Now, it is important to put the degrees in because the 0.24t is actually in radians, and the 144 is in degrees. I see I made a little mistake here. Notice that up here I had b over the one that had the negative j.24, and so this one, and that explains why I was confused about something for a minute. This one is really minus, and this one is really plus. And the sign here, if you looked on the Laplace transform, it has a minus sign right here, and the theta is the theta that goes with the plus sign denominator. And so here the plus sign denominator has the negative theta, and so minus a negative gets a positive. So that's why this one is a plus.